Hello friends, hello everyone, welcome to this channel. This is G Solutions, where we present solutions for your needs. Now I am discussing to you phasors and the functional transformation. It plays an important role in circuit analysis. Let's understand this one, the functional transformation. We transform this to another form. So before we do that, let us first explain. This actually is the name of this curve. This is sinusoidal waveform curve, color in red. Vm sine omega t plus phi. So this phi is actually an angle where it is intersecting the horizontal line before the origin or after the origin. By the way, Vm here is the maximum value here. It is the maximum value where the curve begins to go down and the maximum curve up. So this is taken based on this one, from 0 to this point. This is your V sub n. And for the blue curve, this is the Vm. So you'll notice that if it has a value for phi, which is positive phi, positive angle, so it will be starting here. That phi is here in between 0 and a point of intersection with the horizontal line. You set that to 0. If you make phi is equal to 0 degree, it only gives us Vm sine omega t. So this will be that curve. And exactly it start at the origin. And maybe if you place a negative phi here, your curve will be starting here at a certain point from the origin to this point. So this is the function name of this graph or this curve. Now we have here the general form. For our V, actually what we are looking for here is the value. Let's use this red curve, the value of this point. What is the value here? Can you get the value here? Yes. If you know the time here, when you project that up, it will be intersecting at this curve, so you can get the value of this one. So, you know, for instance, if the value here is t sub 1, you can have actually here v1. And another example, for instance here, let's say this is t sub 2. If you projected that vertically or downward, will be hitting this curve, and this can be your v sub 2 and so on and so forth. So you call this v1, v2 and so on as your instantaneous value. It is the value where you substitute a specific time in this function, because v is varying. As time forwards to infinity, it also varies here, the value of your v. Okay, so the general form for that is v. We use here small caps, and again the maximum voltage. This maximum voltage is multiplied to the sine function where omega t plus phi. And also, if you are going to get the current, we are using here v for explanation, but you can use also I, because it has the same curve, sinusoidal. So we use the small letter I for instantaneous current, and we get the maximum current and multiply that to sine omega t plus phi. By the way, you can transform this form, this sine form, to a phasor form. So what is the value of this one? Well, this is equals to the RMS value, angle or cis, CIS, cosine I sine phi. PRMS, for your information, is actually solved by just dividing it, the maximum voltage, to square root of 2. And it's up to you to research where did square root of 2 came from. So also with your current. The current is IRMS, the root mean square, cis of phi, where IRMS equals to the maximum current divided by square root of 2. I will be showing to you series RL, resistance, and the inductance. Here, we are now using Z as our letter symbol. This is for the impedance. We use Z here because we don't only mean pure resistance, which is R, because Z can involve an inductor or a capacitor, or maybe both, okay, an inductor and a capacitor in series with resistor. That's why the symbol that we are using here is rectangular box. We place Z because this one can be like this one, a resistor in series with an inductor, or a resistor in series with a capacitor, X sub C, or maybe both, and so on and so forth. Okay, this can be that one. So R, XC, XL, XC. Okay, that's why we are using this symbol, rectangular box, and we place Z. By the way, your Z is actually represented in a right triangle. So the hypotenuse is your Z, the impedance, and one leg is for your resistor, and the other one is for the it can either be an inductor or a capacitor. But in this case, we can develop an angle which is theta. That's why we can say that Z is in rectangular form is R plus J XX. It can be like that, or is in rectangular form, or in polar form like this one. Z is of theta. So considering series RL, this one, we have again this instantaneous voltage, which is the maximum voltage multiplied to sine omega t plus let's say let's use phi here, okay, and also for your instantaneous voltage, instead of using Im, I will use Vm over Z. Okay, this is sine omega t plus phi minus theta. Why? Because this one is actually from your Ohm's law. Using Ohm's law, we have V is equals to I sub Z. From Ohm's law, we use I V over Z. But since this has an angle in the denominator, when you place it on the numerator, it will be negative. That's why you have this subtraction of phi minus theta. So you can also solve for Z. We know how to solve for Z there. Again, showing it to you by using Pythagorean theorem. Using this right triangle, you have R squared plus X squared L, or you can have R squared plus, since that your X of L is equals to omega L, you have omega squared L squared. Okay? And for your tangent, we know that tangent here, tangent theta, is equals to X of L over R, and we can get theta as an inverse tangent. You have X of L, since X of L is omega L, that will be omega L over R. We can now the phasor form of this function. So what is the phasor form? Again, we get the V and the RMS, that B is of phi. Okay? And for the current, we have I. Again, this is I RMS is of phi minus theta. So this is how you transform a function to a phasor form. So thank you.